Okay, welcome to our today recitation session. Today we will solve questions about definition of compactness, pre-compact sets, and also questions about sequential compactness. Okay, let me start. The fifth one. Problem 1. Before start, do you have any questions about last week? Okay. Prove that union of a finite number of pre-compact set is also pre-compact, respectively compact. Okay, the first part. Let these sets E sub I be pre-compact sets. A finite number of sets. Let E be union of these finite sets. Okay, mute yourself, please. Ajax. So this each I is pre-compact. This means we can find finite number of points, say, for each I, x I1. I mean, okay. Sorry. First, I need to start like this. Given epsilon greater than 0, we may choose finite number of points. So let's call for each I start with I1, I2 to xi, ki in AI for I equals to 1 to n, such that so EI subset of is finite number of poles. Isn't it? Yes. Okay. As AI is pre-compact. Okay, so it's clear that A is set as an union is a subset of 1 to n, j1 to ki for each I. So, yeah. One and this ki for each I. Sorry, j. A finite set of poles implies what? Implies our set E is in fact precompact. The second part, we will assume this set is compact, so their union also is compact. Okay? Here, let be compact sets. I equals to 1 to n. So let E be this union and assume this sets to alpha. The open cover of our set E implies subset of union alpha U alpha, isn't it? But this set is compact, so there exists finite subcover of this cover, which contains E sub I, isn't it, by definition? So in fact, there exists subcover, say U, I, J, of U alpha such that there are this set E sub I contained in here. K I U I J. Not equality, but subset. Implies the E as an union of these subsets EI 1 to n union. Let me first write subset of n. So J starts to 1 up to where? Ki Uij. Then this set as Uij, 1 less than I less than j, sorry, n. And for each I, we have this j, ki. It's a finite subcover of this E, isn't it? Implies this set is compact. So start the beginning up here. It's a finite set, very compact. Okay. We are done. Do you have any questions about this one? No. Now we will solve questions about which classifies compact subset of discrete metric space. Problem 2. Okay? We will classify compact subset of any discrete metric space. Where is it? Prove that a subset A of a discrete metric space let's say XD, okay, is compact if and only if A has a finite number of elements. A has a finite number of elements. So this part, I mean, the solution of this problem is a problem 2, which has 2 implications. So right-hand side implies left-hand side, and the left-hand side implies right-hand side. We need to show them. But this implication, I mean, right-hand side implies left-hand side is obvious, clear, as any finite set is compact. Okay? This is done in class, okay? As far as I remember. What about the other implication? Assume A is compact in this metric space, discrete metric space. Oh, okay. What about this? So discrete metric space. So we will find a special cover of A. In fact, I can write this A union A in A. So this 1 point sets, but I know if you choose this ball, this set is 1 point, as X is a discrete metric space. So A in A, parameterized by A, this ball, is an open cover of A, implies as A is compact, there exists finite subcover. Let's call this star. Finite subcover, say ball A1, 1, AI, 1 to n of star, i.e. our set is subset of these balls 1 to n as A is finite subset of X. Okay, do you have any question? What about problem 3? Problem 3. Prove that a pre-compact metric space is separable let XD be pre-compact, pre-compact, yes, pre-compact metric space. So XD, recall, XD is separable if there exists countable dense subset A of X. Okay? So we need to construct this A. This A must be countable and dense. But how? Given any natural number, so 1 over n is greater than 0, so we may find finite number of points, let's say, of extent kn, such that our set Ax is a subset of union j equals to 1 to k n both x and j 1 over n. So as X is pre-compact, we have this. Do you have any question? No. Let's choose our A as xij, I natural number, and for each I, j is between 1 j k sub I. Okay? Now, first, must show A is countable. In fact, A's can be written like this. I in N, AI, where AI is what? So, xij, 1 less than j less than k sub I. Okay? A finite set. You know, so A is countable union of finite set. Union of finite sets implies A is countable. And you may find you may write explicitly this function, write explicit surjection. Idea is this. Let k0 is become 0 for any xn j in A, choose m equals to k0 plus kn minus 1 plus j, and define fn as xnj. Okay. Okay. Complete the details, please. So F is surjection. So F is surjection. It means A is countable. Second, A is dense in X. Given any X in X and any epsilon greater than 0. Any X and any epsilon. I will show that, must show both X epsilon intersection A is non-empty. So there exists n0 in n such that clearly epsilon less than 1 over n0, isn't it? I will say n. Then we know X in X, and this is subset of union J equals to 1 to Km mol X M J 1 over N. So this is greater than. So it means dx, there exists some j such that x in both x and j 1 over n, 1 over n, isn't it? So this distance is less than 1 over n less than epsilon. Implies our xmj is in here. Therefore, A closure is X. So A closure is X, it means what? But A is countable implies X is 7. Do you have any question? No. Problem 4. Prove that the completion of a precompact matrix space is a compact matrix space. Compact metric space. So, well, we may use this map isometrically. We may send, that's true, called first, bounded function on X. Then, what's the function? And so, fix x0 in X, some fixed number, sending X to Jx. It's a function, real valued function, dyx, dy x0. And as you have learned in the class, this is a uniformly continuous function. And this G map x to jx is isometry, and closure of gx is completion of if not A, the completion. Completion is unique. Completion of x. Now, as x is precompact, first. Okay. X is precompact, and our G map is isometry. This set Gx is precompact. Sorry. Precompact. I mean, X is both xi epsilon show Gx both you show this Okay, check this. Check. I haven't checked yet, but please do it in the home. Okay, J is precompact, and closure of as this set is complete, then closure of any precompact set is compact. Therefore, completion of x is compact. Okay, do you have any question? No. Okay, ask the other question. Okay. Problem 5. Related to arbitrary intersection of non-empty compact sets. Let X be compact set, compact metric space. Yes, right. Metric space and EM be sequence of non-empty closed sets. Non-empty closed subset of X such that EM plus 1 less subset of E sub M. Prove what? This intersection infinity E M is non-empty. Okay. Assume contrary that intersection n equals to 1 to infinity, EM is empty set. So take the complement of both sides implies X is as a complement of empty set union En complement. So this is open set, open. So this family is open cover of, but X is compact. There exists K1, Kn, and such that X is union Ki complement. Let's choose some M, say, maximum of Ki, I equals 1 to N. So again, take the complement of both sides, we will see this empty set. Ki. But from the inclusion, as n increases, En plus 1 subset of En here, sorry, from here, we conclude that this is En as n is maximum of this chi sub i's. So this is a contradiction as En is non-empty. Therefore, this intersection N is not empty. Do you have any question? No. Problem what? Problem 5 or 6. Problem 6. Problem. We have a sequence in a compact space. Let Xn be a sequence in a compact metric space. In a compact metric space. Space X. If, say, Xn has a single cluster point, point X, show that, prove, limit what? Xn as X. First, note that as X is compact, X is bounded. Therefore, Xn is bounded sequence. So, therefore, if we define sequence of real numbers, An as the Xn X, then An is bounded sequence in here. Buna not diyelim. Birinci notumuz bu. First note. Second one. So X is compact metric space. By sequential compactance, there exists subsequence xkn of xn such that limit xkn exists. In fact, it is x. We will show that. So if x is cluster point of xn, you may consider this sequence as a set, okay? I mean, you may write like this, xn and n. Then x is cluster point of cyst, and this must be in, no, of course, x is another subset. X a cluster point of this set implies, but xkn is convergent sequence, the other subsequence implies we have limit xkn as x. Now, so let me use the first node. So an is bounded sequence in here, this metric space. We have convergent sequences sup inf an, which converges to, let's say, alpha, sup bn, so sup an converges to beta. If an is bounded sequence, then the sequence of inf and sup are convergent from chapter 1. So, and we have what? For all n, sup an less than an, sorry, just say if an less than sup an. So if I am able to show that limit of this, which is alpha, equals to limit of that guy, which is beta, then limit of an is alpha. But in fact, this implies infimum akn less than akn sup akn. So, but akn equals to the xkn x, this goes to 0 as n goes to infinity. Implies if akn sup akn, not this, of course, limit but if an and sup an are convergent, implies all subsequences converge to same limits respectively. Implies, and 0 implies alpha equals to beta equals to 0. So limit an is 0 by sequester. Let me finish the proof. Okay, so an is what? So limit an equals to limit x and x, which is 0, implies given epsilon greater 0, there exists n0 in n such that for all n greater than n0, we have absolute value dx and x 0 less than epsilon, but this part equals to, okay, which implies limit xn is x in this matrix space. Do you have any question? No? Okay, if you don't have any question, let me continue. Problem 7. Let E be subset of bounded circles given like this. Psi m, okay, set of sequences such that absolute value of psi n is less than 1 for all n in n. Okay, prove that A is bounded and closed, but not compact. Now first, nasıl bounded? Clear. For all psi E, let's say it is a psi, and in fact, ball is a zero sequence, so 2 0 sequence. Constant sequence, all elements is 0. Contains our E. So look at this distance. Here we have a submetric, compact, let's say in where, of course, this set Bn. This sub psi 0 equals to supremum psi n minus 0 n in n. But this is equals to psi n and less than 1. All elements of this set is less than 1 implies this supremum less than 1. So this is clearly less than 2, hence psi belongs to this ball. Therefore, A is bounded subset of our space Bn, set of bounded sequences, closed second. Closeness. Okay, we know our ambient spaces Bn is complete. It means E is closed if and only if E is complete. We will show that E is a complete metric space, and hence we conclude that E is closed. Given any Cauchy sequence, psi m, say m in E, i.e. psi m equals to psi m m. And we can write like this for all of them. N in n. Okay, implies this psi m is in fact Cauchy sequence in our set Bn, okay, but Bn is complete. That means psi m converges to psi in Bn. One must show for psi equals to psi n, absolute of psi n less than or 1, which clearly implies psi in where E. Okay. So use, given epsilon greater than 0, there exists m0 and natural number such that the sub psi what? And psi less than epsilon. In fact, the sub 0. Okay. This is epsilon, this is psi m0. Start like this. Psi n equals to for n. Psi n minus psi m0 n plus psi n m0. This is less than or equal to psi n minus psi n m0 plus psi n m0. This is less than supremum as n1 to infinity psi n m0 and 1 to infinity. Alright. 1 to infinity plus psi n m0. Okay, this is less than epsilon. This sorry, do not forget this is absolute. This is less than or equal to 1. Implies our psi n less than epsilon plus 1. This is epsilon some arbitrary positive number for all epsilon greater than 0. But by epsilon lemma implies psi n for all n less than or equal to 1 for all n. Hence, psi is in here, implies E is complete. And what implies this? As Bn is complete, any complete subspace of complete metric space is closed. sorry. Okay. E is complete implies E is what? Closed. Subset of E. Up to you. Do you have any question? No. So third one is not compact. We will find a sequence in E such that any subsequence of that sequence is not convergent. Implies A is not compact. Consider the sequence given like this. Okay? I mean, I-E, E-N. Okay, superscript use N. E-N. This is a canonical delta function. If M is N, then this is 1, otherwise it is 0. Okay? 1 if N is N, otherwise 0. So let A, K, N be any subsequence of En. Then let epsilon be 1 over 2 for all N D sub N L K L. M is not L equals to supremum E K M N absolute. So N in N natural number X is of this and KL. Equals to what? This is in fact, if M is not L, this is 1 as A K M X so A N K L, which is like this N K N N K L. This is if zero, if 1, 1. So, but for all ML, this is greater than our epsilon. It means, therefore, which is a 1 over. Therefore, EM is sequence, obviously sequence in E, but does not have any convergent subsecures. Implies is not compact. Okay, do you have any question up to here? No, let me continue. So problem 8. Problem what? Eight, yes. Problem 8. A is closed. And B is compact. 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 The proof A intersection B is compact. First note that if A is B is compact, then it is closed. Huh? B is compact implies so B is closed. Therefore, A intersection B is closed. So U equals to complement of this intersection is opening some ambient space X. Okay, which contains A and B. In X. Open and X. Okay. So let's U alpha be open cover of yes A intersection B. Then this sets U alpha in a union. One more open set is an open cover. And is an open cover of what? B. But B is compact. There exists finite subcover of given cover, let's say Xi, and star subcover W U alpha E may contain U or not if A intersection B is B, then of course it's compact, so contains this is subcover of star. May contain or not, as here, as U alpha union U. So a finite subcover may contain or not is U, but it's not so important. Again, Without U or with U, it's a finite subcover. So as A intersection B intersection U is empty, implies our A intersection B is contained union U of I. So U of I and is finite subcover. Cover of U alpha implies A intersection B is compact. Do you have any question? No. Problem what? Problem 9. Problem 9. For two subsets A and B of R, real numbers, let's we have this set A plus B, A in A, and B in B. Okay. If A and B are compact, then their sum is also compact. Prove that this set is also compact. The second part of this question is if A is compact, and B is closed, prove that A plus B is closed. Okay, the first. Assume A and B are compact. We have two compact sets. Let Xn be sequence. I will use the sequential compactness. It is the arbitrary sequence in A plus B. Then Xn is An plus Bn. Natural number implies In sequence in A, Bn sequence in B. Okay, as A is compact, there exists subsequence convergent of, say, Akn of An with limit Akn is A and belongs to set A. So therefore, Xkn can be written like this, is subsequence of Xn. Okay, Ekn is sequence in compact set compact set Bn, not compact set is B, not Bn. Compact set B, there exists convergent subsequence. So BLKN of BKN such that limit of LKN is B, belongs to set B. Okay, now as ALKN of is subsequence of convergent sequence AKN, we have limit ALKN is A. So limit XLKN, which is limit ALKN plus BLKN by limit rules is sum of the limits, limit of the sums ALKN plus limit BLKN. This is A plus B. And implies Xn has convergent subsequence XLKN such that limit XLKN, which is X and belongs to A plus B. X is here. X equals to A plus B. Forget X. A plus B. Therefore, A plus B is compact. Okay, we start two compact set in real numbers, then their sum must be compact. For second part, assume what? A is compact, B is closed. A is compact, this time B is not compact, not need to be compact, but closed. And B is closed. Okay. We will show that A plus B is what? Closed. Let X belongs to A plus B closure. This means there exists Xn equals to An plus Bn sequence in A plus B such that Xn converges to X. Okay. As A is compact and and this An is sequence in A, there exists convergent subsequence AKN of An such that limit AKN and belongs to A. Okay. Consider subsequence XKN, which is AKN plus BKN of Xn. Then clearly BK sub n equals to xk sub n a k sub n. As limit xn is x implies limit xkn is x. And any subsequence of convergent sequence converge to same limit. Okay? So implies limit bkn is limit xkn minus akn by limit rules x minus a. Oh, so I need to show this belongs to B. But how? As B is closed and bkn sequence in B with bkn converges x minus a. X minus a belongs to B closure, but B closed, which is B, implies so x belongs to a plus b. Therefore, our set a plus b is closed. Up to you, do you have any question? Okay. Question 10. We have such a sequence in Cartesian product of metric space BP. Niye böyle vermiş ki? Is sequence in R. And suppose there exists M1, Mn, sub n such that pi pi p is equal to mi for all e and for all p op goes like this, where Vp equals to V1p, V2p, Vnp. Prove that Vp has a convergent subsequence. Okay. Note that here in R we have a absolute metric space, and I take this metric space like so. Okay, then Vp V. So P goes to infinity, okay? So you know this origin less than always epsilon. So AV, I will define this set, subset of ball of 0 is 0 epsilon. AV is this set. VP, P equals to 1, 2. Okay. So implies AV is bounded, implies AV closure is bounded and closed by Henry-Borel theorem. AV closure is compact. Sorry. AV is compact, closure is compact. This is obvious, check, but it's obvious. So the VP sequence in AV, so in fact AV closure, but AV closure is compact, implies VP has convergent subsequence VKP in AV closure, and limit VKP as P goes to infinity belongs to AV closure. Up to you, do you have any question? No? Let me make some reminder in the last week. Okay. In fact, I will make a correction from last week. It was so difficult question. Example of discontinuous function which is additive. Discontinuous real valued function on R which is additive, i.e. f R2 R is discontinuous in somewhere, but it is additive. So last week I tried to make a R as a direct sum V. Last week I defined V, which is obviously is a 0. Okay, only contains 0. Then it is not a direct sum, but I will write it as a direct sum where V is Q vector subspace of R. How? I define V as X mod Q, X in R, real number. I mean, for example, this is a rational number. Sorry. This is not V, but So implies. Okay. Similarly, but from these examples clearly implies Q intersection V is only contains 0. Any rational numbers Q, and for all Q mod Q is 0. And we write like this here. Mod Q equals to square root. So 0 belongs to here. Show V is vector space, and now given any x in R, x mod Q is in V, and then clearly x minus x mod Q belongs to Q. So x minus x mod Q plus x mod Q belongs to Q plus V. So implies our set of real numbers can be written like this. Also, you may see from here, in fact, the isomorphic to as a Q vector space R over Q. But how? So we have a grad course. Maybe you have seen, I don't know, Q real numbers R over Q. As far as I remember, any short sequence of the short exact sequence is reminder, not related to this course. We have defined as R Q plus V, but let me make precise this V. It's not so important. Any short exact sequence of vector spaces is split. Okay, is split means, and you may find like a function sending R to R mod R minus Q. So composition of these two functions is identity on Q. Q, R, Q, which is identity function, implies this short exact sequence is split, i.e. R can be written like this. As far as remember, any short exact sequence of vector spaces that's split. Okay. It is not related to this course. Okay, if R is like this, and define function as f R, which is Q plus V, send it to Q. Then f is continuous but sorry, F is additive but not continuous. You may see in the PDF file which I have sent you to last week, okay? So this is all for today. We will continue next week. Now I'm stopping the sharing and also I'm stopping the recording. Stop.